Welcome to the introductory lecture for Data Science for Psychology and Neuroscience at Carnegie Mellon University. In this opening lecture, I'm going to go over the idea of data science as a form of quantitative epistemology. The readings for this lecture are Fred Dretske's A Précis of Knowledge and the Flow of Information, and Vlastelica's blog post on empirical risk minimization. If you haven't read these, pause, go read them, and come back. In today's lecture, we're going to go over 4 broad topics. First, I'm going to go over what is data science. Then I'm going to go over information flow and knowledge, showing basic forms of epistemology and thinking about knowledge that we can tie back into data science. Then I'm going to formally present an idea of data science as epistemology. And then I'll end by giving you an overview of the class. Let's start by answering the question, what is data science? This is a data point, xi. Say hello. This is the ith observation of variable x. And our little friend xi has another friend, yi. This is the ith observation of another variable. And what we want to know, fundamentally, is what is the relationship between x and y? But in data science and statistics, we don't just look at these variables alone. We look at them in the context of their friends. So we might have our observation xi be part of a matrix where every column is a set of different variables. We'll call those features. And every row is a set of observations that are all tied together. And so we can have our matrix of friends of x's. And we want to understand how this collection of x's relates to a collection of another variable y. So now we have y in a vector with his friends too. Now, to simplify things, rather than showing the matrix form, what we'll just do is use the capital letter notation to indicate matrices. So this is the same way of showing what I showed above. We want to understand how the matrix of x projects to or associates with the vector y. And in statistics, we don't just want to know generally the relationship, we want to formalize it. So we describe this relationship this way: y equals f of x. How do we take a function to transform x into the best projection of y? This is the fundamental form of all of statistics and machine learning. Even things like unsupervised learning, where there is no y, is essentially this form, but where y equals 0. Now, throughout this class, and any class you take in machine learning, statistics, data science, we talk about this relationship between x and y at 2 different levels, and we move back and forth. So it helps to pay attention as to what level we talk about. At one level, there's the truth. The true relationship between the variables x and the variable y. The full distribution, the whole population of x and the whole population of y. It's the reality of the world, what those true forms of the relationship are. We also describe this relationship at the experiential level, also known as the empirical level. This is what we can actually work with in data science. These are empirically collected observations and our understanding of the relationships within our limited sample. Now, when we talk about the relationship between x and y at the level of truth, we refer to this relationship as a concept class. A concept class is a set of true functions, we'll use the term f here, that describe the structure of x and his relationship to y. On the empirical side, in the experience realm where we can collect data and hold on to and tangibly touch it, we have the hypothesis class. So this is the same relationship, except now we're going to refer to a set of candidate functions that describe the structure of x and its relationship to y as a set of hypotheses. So 2 different ways to describe the same relationship. And when we're talking about the experiential realm or the empirical realm, we'll sometimes refer to it as h of x, the hypothesis about x that projects to y. And the fundamental goal of data science and statistics is to approximate with your hypothesis the true functional form. So you want your hypothesis class, your set of functions that describe the structure of the relationship between x and y that you have, to be as close as possible to the concept class, the true set of functional relationships between x and y. So going back and taking a step back, what is data science? It's an interdisciplinary field that uses scientific methods, processes, algorithms, and systems to extract knowledge and insights from many structural and unstructured data. This is your standard Wikipedia definition. Another way to put this, however, is what could I know from my data? What can I learn from my data? And to answer this question, data science itself leverages three broad areas of understanding from science and academics. So data science is an engineering field. It has a goal of building, in this case, building models and tools for understanding your data. It is a science. It's got the word science in its name, and it has a principal function of understanding the relationship between x and y. There's also an aspect of communication. So there's an art and design component to data science as well. How do you effectively communicate these complex relationships using either statistical models or visualization? And so you can think about data science as being the intersection of computer engineering, graphic design, and statistics. So in the Venn diagram of these three broad fields, data science sits here. But data science isn't the only overlap between these various fields. So for example, the overlap between graphic design, which focuses on visual organization, aesthetics, and intuitive design, and statistics, which focuses on models, hypothesis tests, metrics, and measures, you have the field of data visualization. At the intersection of computer engineering, which focuses on data formats, data architectures, and computing speed, with graphic design, you have the field of rendering. And within the intersection of statistics and computer engineering, you get machine learning. So essentially, data science is a variant of machine learning that also allows for using graphic design tools as another means of communicating and understanding the relationship between x and y. This is data science in a nutshell. Now, data science itself, because it has a strong scientific component, is focused on building towards understanding. And to understand this process and what this goal is, I think we have to take a step back and take a deep dive. Well, okay, let's be honest. This is going to be a shallow dive on a deep literature on the relationship between information, knowledge, and eventually understanding. So let's put on our philosophy hat, shall we? Let's dive into first the field of epistemology. Epistemology is this branch of philosophy focused on answering the question, what is knowledge? Within epistemology, there's a subfield known as naturalistic epistemology, which views knowledge as a natural kind that is accessible to science. Basically, naturalistic epistemology strips away all the metaphysics of traditional epistemology and focuses on what can we tangibly know through empirical experience. Within naturalistic epistemology, there's a subfield known as reliabilism, which arose in the latter half of the last century. And in reliabilism, knowledge is seen as arising from the establishment of beliefs based on the reliability of information sources. And I want to focus on reliabilism because its philosophical theoretical form most closely resembles the theory and structure of statistics and machine learning. And in particular, I'm going to focus on the work of this man here, Fred Dretske, who really took the first steps on trying to build a formal computational level theory of knowledge and how it arises from information sources. Now, to understand Dretske's theory, we have to get a little bit of knowledge on the fundamentals of information theory. Information theory itself is a formal field of mathematics and computer science with the goal of developing a formal theory for the transmission, processing, extraction, and utilization of information. You can boil most of information theory down to this relationship here. You have a signal, you have a receiver, and you have the channel that relays the signal to the receiver. And the approach that information theory takes is to use mathematics to quantify the amount of information a channel can convey about a signal to a receiver. Let's look at this a little bit more closely. First, let's look on the signal side. The question that information theory wants to answer on this side is, what is the average amount of information conveyed by the signal itself? And according to Shannon's information theory, you can describe that using this equation, which states that the information for signal S is the negative sum of the probability that the ith state is observed, that's that P of Si, times the information available from the ith state. So what's the probability? Let's say we have a signal as binary, 0, 1. What's the probability that the signal is in the state 0, or what is the probability that's in state 1? The probability is easy to understand. This information available part of the equation is a little bit trickier. And the trick that Shannon came up with is to think about information as being related to the surprise of the state. So the more surprised you are by the signal being in state Si, the more information it contains. And if you think about it that way, then we can relate this back to the probability of the state itself. So you can represent the information available when the signal is in state I as the log of 1 over the probability of being in state I. Now, how does this work? Okay, let's say that I of Si represents the amount of surprise you have when the signal gets in that state. If you have a state that's always happens, so let's say that the probability of the signal being in state I is 1. It's always in that state. It's always a 0. Then there's no surprise to seeing it in that state. It's expected. As we lower that, get it down to 0, well then the amount of information and the amount of surprise moves towards 1. So rare probabilities of specific states equals more information. And so what we do with information theory is we replace this I of S of I with log P. So you'll hear Shannon's information as being P log P. The probability of being in state I times the log of that probability of being in state I. And I'm using log base 2 here because this is typically used in binary systems. So your base logic is either 0 or 1. Let's consider a simple example, a fair coin toss. Now the probability of the coin being heads is 50%, or 1/2, and the probability of it being tails is also 50%, 1/2. So we can use Shannon's equation to calculate out the bandwidth of information conveyed by a coin toss, just by applying the formula above. So the information conveyed in the coin toss is negative 1/2 times the log of 1/2 minus 1/2 times the log of 1/2. First part is heads, second part is tails. That boils down to negative 1/2 times negative 1 minus 1/2 times negative 1, which comes down to 1 bit. So the amount of information conveyed by a fair coin toss is exactly 1 bit. Now this is on the signal side. Let's look at the receiver. Well, we can apply the same logic to answer the question, what is the average amount of information received by the receiver? It's the same functional form. You have the information for the receiver, I of R. You have the probability that the receiver is in the ith state times the amount of information available from the ith state using the exact same logic. Now, we have information at the signal, information at the receiver, but the critical factor here is how does this change across the transmission? Because I of S doesn't necessarily equal I of R. The information that's in the signal itself doesn't necessarily mean that you're going to have the same information states in the receiver. It's because there might be noise or disruption in the channel itself. So we also want to think about a third probability. We have our information at the signal, we have our information at the receiver, but most importantly, we want to look at the mutual information between the signal and the receiver. And this reflects the amount of information transmitted across the channel. Now, if you have information of the signal, from the signal, and information at the receiver, then the concept of the mutual information is just, you can infer it automatically, right? So it is essentially the overlap of information between the signal and the receiver. What is not explained by the mutual information, if it's on the signal side, we'll call it equivocation. So this is uncertainty in the information being transmitted. On the receiver side, we call it noise. So it is the disruption of the signal through the channel that becomes ambiguous on the receiver side. And the mutual information is the information transmitted from S to R, and it's the total amount of information available at R minus noise. So we can represent the mutual information as just the information of the receiver minus noise, or conversely, information of the signal minus equivocation. This basically sets us up now for trying to understand how information theory gives us an understanding of meaning and knowledge, at least according to Dretski's framework. Let's take a look at Dretski's theory of information and knowledge and meaning. What Dretski wanted to answer is, when does signal S indicate a specific state of the world F? Now, you notice from my description of information theory before, we're talking about average amount of information conveyed by a channel or a signal or a receiver. But that doesn't give us any access to meaning. We can think about meaning of information as being the unique states and how they map to some purpose. So for example, let's say I wanted to understand when the signal is greater than or equal to 5. We want some meaning to indicate that the signal state is above some arbitrary unit 5. So we'd have a vector of information. So we'd have the signal for n different observations. We'd have the state of the receiver for those n different observations. We want to see how much the receiver state tells us about whether or not the signal is greater than or equal to 5. So let's just fill this in with some arbitrary numbers at the moment. Now, in a perfectly veridical system, the probability of R being 1 is perfectly related to whether or not S is greater than or equal to 5. So if we plot S on the x-axis here and the binary state of R on the y-axis, if R was truly conveying knowledge of the state of the signal, and in particular, if you can use R to infer the meaning that S is 5, you should have a relationship that looks like this. It should just be a quick transition from 0 to 1 as soon as S crosses from state 4 to state 5. This concept here is what Dretski defines as knowledge. When you have this relationship, you fundamentally have knowledge. In Dretski's terms here, he says that a signal R at the receiver carries the information that S is F if the conditional probability of S's being F, given R, given the receiver, and something known as K, which is your prior knowledge, is 1. But with just K alone, which is that prior knowledge alone, it has to be less than 1. This is Dretski's formal theory of knowledge represented in information theoretic terms. Okay, let's take a closer look at this here. According to Dretski, we have a signal. And the signal, if you're referring to the receiver as being an agent, leads to a set of beliefs. So these are beliefs about the state of the signal, some input. And those beliefs lead to a particular set of actions, which we'll call A. And the information conveyed is represented by the mutual information between the signal and the receiver, in which case, if it's an intelligent agent like a human being, is a belief. And that gives you the degree of information that is being conveyed. But for knowledge's sake, what Dretski says is that essentially there has to be perfect mutual information between the signal and the receiver. There has to be zero equivocation or zero noise in order to consider this belief a form of knowledge. And in Dretski's term, he changes that B to a K to indicate when you've gone from something with belief, which is zero uncertainty, to knowledge. Now, what I want to show is that this form, this framing of the nature of knowledge in information theoretic terms actually has a beautiful symmetry to the way we look at relationships in data science, statistics, and machine learning. That S to k, or S to b, has a very similar form as what I showed at the beginning, this f of x equals y, or y equals f of x. So in this case, you can think about x as being the signal, y as being the receiver, or the beliefs or the knowledge, and f is reflecting the mutual information between the two. And in statistics and data science, the action that we take is a decision. We make a decision about the relationship here, given our data and some hypothesis, which reflects the degree of information between the signal and the output. And that gives us, if we're working with statistics, it's a hypothesis instead of an F, so we're going to be dealing with hypothesis class, yada, yada, yada. But you can see at least the emergence of this symmetry. Now, what I'm going to do in this next phase of the class is build off of Dretski's idea and expand it into the case where you allow some degree of uncertainty in the definition of knowledge itself. Now, this is where I'm going to push data science as a form of epistemology. However, to understand this, we need to take another step back and look at the theoretical basis for all of statistical learning and machine learning. For this, we have to go over a concept known as risk. Now, risk is the amount of information lost, or the amount that's lost in your model of the relationship between x and y. So the risk of a hypothesis h is determined as the loss function between h of x and y. And in this case here, you can think of h of x as being your y hat, your prediction. So the less loss you have, the lower the risk. And what that really means is that the risk of making a decision about y from x gets lower as this error between the hypothesis and y itself gets smaller. When you have continuous data, so working in contexts like normal linear regression, this loss function can be just the squared error, so the difference between your prediction and the observed value of y squared, a very common loss function in statistics. When you're dealing with categorical data like classification problems, it's the error, so the probability of y hat equaling y. Both of these just reflect variants of loss functions that reflect the risk of your hypothesis. And the learning theory that underlies most of modern statistics and machine learning is known as empirical risk minimization. And the idea of empirical risk minimization is actually quite simple. We say that the expected risk of a hypothesis H, given n observations from a probability distribution P, is just the integral of that risk over the probability distribution. So you have a distribution of x and y, you have a hypothesis, and you have some loss function, risk, that you just sum across all of your data points. Very simple. Now, in most contexts in psychology and neuroscience, a lot of times we just stop where the probability distribution is what we're calling a training set. So we have some data we collected, we calculate the risk that's essentially fitting your model to your data, and then we make inferences off of, let's say, the parameters of the hypothesis. So in this case, maybe your linear regression model is your hypothesis, and you'll calculate over your risk, the loss, you try to minimize it, and then you say, okay, with this best fit model, what are the regression coefficients? Are they above or below 0? But in statistics and machine learning, we don't stop in this one distribution. Actual empirical risk involves integrals over two distributions of data. The first distribution, shown in magenta here, is the training distribution. It's the same as what I showed above. But you also have to calculate this risk for true ERM over a second distribution of data. We call this the test distribution. That's shown here in blue. So the overall empirical risk of your hypothesis, given observations from a probability distribution, is the risk not only over the set of data you use to train your model or train your hypothesis, but also how well that risk generalizes to unseen test data. And the test data isn't used in training. This is validation sets. That's untouched, pure form, basically prediction error. Now, the critical assumption of empirical risk minimization is that both the training and the test data come from the same distribution. There's some hypothetical real-world distribution shown here by this red probability distribution from which both the magenta and the blue distributions are sampled from. We call this the IID assumption, which stands for independent and identically distributed data. With this assumption on empirical risk minimization, you can actually calculate out now the sample complexity, how many observations you need, and the learnability of any individual class of hypotheses. So essentially you can determine what is learnable and the time it would take to learn. Our current best understanding of these limits falls under the area known as probability approximately correct learning, or PAC learning. PAC learning is a goal or an attempt at answering the question, what is learnable? What are the limits of what we can learn given a particular algorithm? And for PAC learning, it requires the learner to approximate the true hypothesis of the data, the true H, and be as computationally feasible as possible. And we use P versus NP here to describe whether or not it will take polynomial time to calculate out the answer, or non-deterministic polynomial time, NP. Things that are calculatable in or computable in polynomial time, P, are accessible to us. That means that we can solve the problem, where we can learn it in a feasible amount of time. And not all P-hard problems are actually learnable. Some are exponential, but it would take, let's say, a millennia to execute. So that's practically learnable, but not necessarily, or theoretically learnable, but not necessarily practically learnable. And everything that's NP hard is just impossible for us to learn. So what PAC learning does is it wants to know what's the kind of limits to which I can understand how many observations I need, your power, and what's the feasibility of learning. The brilliance of PAC learning formulation for determining the limits of learnability is that you can boil everything down to this simple equation here. So it's a little bit complicated. It's a reformulation of what I showed just in the previous slide. So here, this P of D is just across a probability distribution. So it's the same double integral I showed in the last slide. But in this case, what it's saying is that any theoretical hypothesis with a theoretical expected risk. So this is the ground truth in the real world on that truth level that I talked about at the beginning, relative to the empirical risk itself. So this is what you actually calculate with the data you have. That's why there's the little hat over the H here. If you can, with a given set of data, have the difference between what you observe, the empirical risk, and what you should hypothetically get, the expected risk, less than some error term epsilon, well, that gives you the approximately part of the equation. So this is approximately correct. Your epsilon determines the degree of leniency you're going to have for determining whether or not your expected risk is as close to the true risk as possible. I'm sorry, I said expected risk, your empirical risk. So it gives you essentially how close or how approximate your true empirical risk is to the ground truth. The probable side for PAC learning comes on this right-hand side here. So imagine you solve, or you collect data, you calculate an empirical risk, and you calculate this relative ratio to a ground truth. And these are some assumptions here that I don't have time to go into the details of. So over time, the probability of you observing this difference less than epsilon, 1 minus delta times, gives you your certainty or the reliability of being able to learn that hypothesis reliably. So in this case, your delta term is a leniency for the probability of observing being this good, being below your epsilon threshold. The brilliance of framing learnability in this way is that you can now calculate out the sample complexity, how many observations you need in order to solve a particular hypothesis. It determines what is learnable. Now, what I would want to argue here is that this learnability gives us a working definition of knowledge that allows for us to better understand the world. Let's rethink what is knowable. Recall that Dredske said that a signal at the receiver carries the information that S is F if the conditional probability of S being F, given R, is 1. In other words, if there's no equivocation, if there's complete mutual information between the signal and the receiver, that's the only case for Dredske where you have knowledge. Everything else is simply a belief. However, we can reformulate this from a statistical learning perspective and say that a signal y carries the information that x is f if y equals f of x is learnable. If you can learn, according to empirical risk minimization and statistical learning theory, a relationship between x and y, you have an atom of knowledge about that relationship. And the beauty of this is it not only relaxes some of the constraints of knowledge relative to Dredske's framework, but it also makes knowledge a continuous function. So you could have a model of the relationship between x and y that fits reasonably well, generalizes okay, but well above chance, and that gives you a specific degree, rather small, of knowledge. The better the model, the more extensible it is in terms of understanding the relationship between x and y, the more knowledge you have. So we not only have the existence proof of knowledge, but we also have an evidentiary proof of knowledge as well. As long as this relationship is learnable, you can gain knowledge, and it reflects the degree of knowledge. Let me formalize this a little bit here. For the sake of this course, I'm going to say when you fit a model, so when you calculate out the risk of the model or the hypothesis over the training distribution, you have a sense of the information and meaning conveyed in the relationship. When you add in that outer integral, when you can evaluate how well your learned model generalizes to new data subject to that IID constraint, the independent and identically distributed constraint, then you have knowledge. The better you are at generalizing to the test data set, the more knowledge you have. Now, what about that tricky concept of understanding? Understanding is a little bit unique. When we understand things, we are able to use that knowledge in new contexts. So I'm going to define understanding here as being the case where you're calculating out the expected risk of a hypothesis given a distribution of data where you have the data distribution that you learned your model on, and the generalization is applied effectively to a new distribution of data that is not IID. And what I mean by that is this new this new test set might be correlated with the probability distribution you trained your data on, that you learned your model from, but not perfectly identically distributed. And that degree of generalization outside the probability distribution that you sampled your data reflects the degree of understanding you have about the relationship between x, y. So the more we can generalize to new data contexts, the greater the degree of understanding we have of the relationship between x and y. And this is where we kind of hit the limits of data science, or at least current data science, and speak more broadly about the field of science itself. Now, this framing of understanding that I have here is known as out-of-distribution learning in statistics and machine learning, and there's a lot of really beautiful work being done over the last few years on this problem. But I think as a field, when we're using statistical tools to understand the world, we don't necessarily need to rely on neat statistical tricks to do out-of-distribution learning. Really, where this generalization can happen is in the space of theory itself. Now, traditionally, most scientists follow the hypothetico-deductive model of science, where you have this loop between theory, hypotheses, physical observations, and generalization that builds a high-level conceptual model of the world that advances our understanding of whatever system we're trying to study. This model was somewhat independently described by both Popper and Hempel back in the 20th century, and is the kind of general gestalt understanding that we have of the process of science. And I'm going to show you how this moves us towards that problem of understanding. So in this cyclical logic, which is sometimes called the Wallace wheel, theory uses conceptual models to deduce consequences and make predictions of relationships in the world. So theory in this case is a very abstract notion. A classic case of this would be the theory of evolution, right? There's no tangible, in the high level form, there's no kind of tangible empirical parts of that model. It's just a high level idea. But you can operationalize your definitions and form very specific hypotheses that you can then use to design tests and collect specific observations. So you'll get those observations. And then using data science tools, we determine the outcome of these observational tests and infer some sort of consequences from them for generalization purposes. And then you can use that generalized knowledge to reframe concepts or redevelop propositions in order to refine your theory. So on the right-hand side, we have deductive reasoning, which is trying to kind of pare out the complexity of your logical relationships, and we'll go over this in a later lecture. On the left-hand side, you have the inductive reasoning designed to build and refine your theories. And data science sits on this lower part of this wheel. Data science allows for us to formalize our hypotheses in a testable manner, develop ways of understanding our observations and the information in our observations, and learn inferences that allow for generalization. And the understanding part comes from the top. It's high-level theory that now can make generalizations to new contexts, which result in new hypotheses that you can kind of test again and again and again. This idea now between information, knowledge, understanding frames the way that I've structured this course. So we're going to start by trying to understand the nature of information. How do we learn the structure embedded in our data? Then we're going to move on towards the concept of knowledge. How do we gain knowledge about the relationship between X and Y? Or more precisely, how does the structure in our data predict observations? And then finally, the last part of the course is focused on scientific theory. How does our knowledge generalize to new contexts? And this gives us our understanding. Hopefully by the end of this course, you'll see how we can go from each of these stages, understanding our information, gaining knowledge from those relationships, and using that to generalize a greater understanding of the world. This is our goal, and this is how data science serves as a form of epistemology. Okay, so let's take a look at what we're going to be doing over the next semester. I'm going to do a quick overview of this course here. The goal of this class is to show how data science approaches can be useful for revealing information and knowledge from observational data, just like what I went over in the previous part of this lecture. The learning objectives for this class are, first, to understand basic principles of statistical theory, measurement, and experimental design, be able to clean and organize data effectively, be well versed in the execution and interpretation of data analysis, use information resources to find appropriate data science tools, communicate statistical results effectively in multiple modalities, and to be a critical consumer of data science techniques and their application in empirical research. What do you need to know coming into this class? Just a basic level understanding of probability theory and statistics. If you're at Carnegie Mellon University, this is gone over in 36309 or 86309 or similarly equivalent courses. Basically, do you know what a mean is? Do you know what variance is? Do you know what a simple correlation is? Have you seen a t-test before? If you answered yes to all those questions, congratulations, you're qualified to take this class. It would help to also have some basic familiarity with R or similar functional data analysis languages, although this would only be helpful. Hopefully along the course, if you don't have much exposure to R, you'll be able to learn the techniques along the way. Now, how is this class structured? There's a 3-part structure to each class. Prior to every class time, you're expected to do the reading and watch a 30 to 40 minute lecture like the one you're watching now. Then when you come into class, we're going to do, at least during the synchronous portion of the class, we are going to do a short question and answer period and an overview of the lectures and the readings. Very short, brief, make sure we're all on the same page. Then what we're going to do is do breakout discussions. There are discussion questions associated with each class. We're going to choose one, and as in sets of small groups of 4 to 6 people, we're going to discuss answers or try to come up with answers to the discussion questions. And then at the end of class, we're all going to come together and the groups are going to present their answers. And we're going to try to collectively and dynamically come to some understanding of the content of each class. Then afterwards, after class, there is a Jupyter Notebook tutorial tied to the Jupyter book of this class called Data Explorations, and some associated homework exercises designed to re-solidify the content for each course. So we've got two general learning goals with this flipped kind of design. First, we want you to learn content knowledge, which is crystallized knowledge, prior to coming into class. And then during class, we're going to use dynamic discussions to develop fluid intelligence of the content. What are the text and resources for this class? There's a Jupyter book called Data Explorations, found in this URL here. Our only textbook for the course, although it only really covers about half of the course, is James Whitten, Hastie, and Tibshirani's An Introduction to Statistical Learning with Applications in R. We're using the second edition right now. You can find it here on the URL on the screen. It's also helpful but not required to have R for data science. It's an O'Reilly book. It's a really good resource for, in particular, working with the tidy data universe, which we'll go over. There are also auxiliary readings in the form of PDFs that are on the class Canvas and GitHub, and this goes over material that's not covered in the main textbook. You can find all the information of the course in the course's GitHub repo, which is shown here. So it's github.com/coaxlab/datascience-psych-neuro. And in particular, I want to point you to that resource because the wiki page on the GitHub repo has lots of useful links for helping you get started and help you kind of learn how to kind of work with this class. Okay, that's it. I wanted to just do a general overview at the end here, make sure we're all on the same page. I hope by this time you can see that data science can be seen as a branch of epistemology, revealing how meaning and knowledge can be determined from information, from your data. And that these approaches fit into a larger process of scientific discovery that links abstract theories to empirical data. And the goal of this course is to learn how to gain insights into the information you have, develop knowledge, and develop further understanding of the relationships of interest in your data.